Albert Einstein was wrong once in a very specific and very important way, and the story of how he was wrong, and how we found out he was wrong, and what it means that he was wrong is one of the most extraordinary stories in the history of human knowledge. It is a story about the deepest question physics can ask. What is the universe actually made of? At the most fundamental level, when you strip away everything that is an approximation or an averaging or a practical convenience and get down to the bedrock of reality. It is a story about two of the greatest minds of the 20th century arguing for decades about whether God plays dice. It is a story about a theorem so simple it fits on a page and so deep it took 20 years for the physics community to appreciate what it meant. And it is a story that ends in a laboratory with a measurement so precise and so careful that it leaves no room for doubt, confirming something so strange that even the people who expected it to be confirmed find it disturbing to contemplate. The thing it confirmed is this: the universe is not local. Two particles, once they have interacted, can remain connected across any distance in such a way that a measurement performed on one of them instantly affects the other, regardless of how far apart they are, regardless of whether any signal could have traveled between them in the time between the measurements. This connection, this entanglement, is not a signal. It does not carry information faster than light. It does not violate special relativity in any practical sense. And yet it is real, it is measured, it is used in technologies being built right now, and it means that the universe at its most fundamental level is deeply, irreducibly, inescapably non-local. That distant things can be connected in ways that no picture of reality based on objects with definite properties existing at definite locations can explain. Something is wrong with the most basic assumptions we make about how the world works. And Einstein, who made those assumptions more carefully and more explicitly than almost anyone, spent the last 30 years of his life being certain that quantum mechanics was the thing that was wrong, and died not knowing that he was the one. To understand why entanglement is so strange, why Einstein found it so unacceptable, why it took decades to confirm it experimentally, why the confirmation matters so profoundly, you have to understand what quantum mechanics is saying about the world, and why it troubled Einstein so deeply, and why his trouble was not the trouble of a man who did not understand the theory. Einstein understood quantum mechanics perfectly. He helped create it. His trouble was the trouble of a man who understood it too well. Quantum mechanics was not developed by one person. It grew in the years between roughly 1900 and 1927 from the contributions of an extraordinary collection of minds: Planck and Einstein and Bohr and Heisenberg and Schrödinger and Dirac and Born and Jordan and many others, each piece building on the last, the theory taking shape the way a sculpture takes shape, chipped away from the stone of classical physics, until what remained was something that nobody had anticipated, and that almost everyone, including its creators, found deeply puzzling. The theory that emerged was extraordinarily successful. It predicted the behavior of atoms and molecules and light and chemical bonds with a precision that classical physics could not approach. It was the foundation of the transistor and the laser and the MRI machine and the LED and essentially every technology that has defined the modern world. There is no serious doubt that quantum mechanics is correct, not just approximately correct, but precisely, spectacularly, breathtakingly correct, tested to more decimal places than any other theory in the history of science. But what does it say? What picture of reality does it paint? This is where the trouble begins. Quantum mechanics describes the physical world in terms of a mathematical object called the wave function, a function that encodes, for every possible configuration of a physical system, the probability amplitude for finding the system in that configuration when you measure it. The wave function evolves smoothly and deterministically over time according to the Schrödinger equation, spreading out and interfering with itself the way water waves spread and interfere. But when you actually measure the system, when you look at it, when you interact with it in a way that extracts information, the wave function suddenly collapses. The spread-out probabilities collapse to a single definite outcome. The particle that was spread over many possible positions is suddenly found at one specific position. The electron that had a probability of being spin up and a probability of being spin down is suddenly definitely spin up or definitely spin down. This collapse is instantaneous. It is not described by the Schrödinger equation. It is an additional postulate, the measurement postulate, added to the theory to bridge the gap between the smooth evolution of the wave function and the definite outcomes of actual measurements. And it raises a question that quantum mechanics in its standard formulation does not answer: what is the wave function? Is it a description of something physically real? Is the quantum state of a particle something that actually exists in the world, spread out over many possible positions until measurement collapses it? Or is the wave function merely a mathematical tool, a bookkeeping device that encodes our knowledge of the system, not the system itself? Is quantum mechanics a theory about reality, or a theory about what we can know about reality? Einstein believed, with a conviction that was both philosophical and physical, that the wave function was not a complete description of reality. He believed that there were hidden variables, real physical properties of particles that quantum mechanics did not describe, that determined the outcomes of measurements in advance, that were merely unknown to us and therefore appeared random. The randomness of quantum mechanics, in Einstein's view, was like the randomness of a coin toss, not fundamental, not a feature of reality, but a consequence of ignorance. Underneath the probabilistic wave function, Einstein believed there were definite values. The particle really did have a definite position and momentum. The electron really did have a definite spin before any measurement was made. Quantum mechanics just did not know those values. They were hidden. Find the hidden variables, and you would recover a deterministic, local, sensible theory of reality in which God did not play dice. The argument between Einstein and Niels Bohr over this question is one of the most famous intellectual disputes in the history of science. Bohr led the Copenhagen school, the view that the wave function is complete, that quantum mechanics is a complete description of what can be known about physical systems, and that the question of what the system is doing when it is not being measured is not a scientific question but a meaningless one. The moon is not there when nobody looks, in the Copenhagen view, or rather, that question has no answer, because the moon when nobody looks is not a well-defined physical concept. Einstein found this view philosophically repellent. He believed in a reality that existed independently of any observer, a reality that had definite properties whether or not anyone was measuring them. He could not accept that the act of measurement brought properties into existence rather than revealed properties that already existed. The debate was conducted in seminars and in letters and at conferences, most famously at the Solvay conferences in Brussels, where Einstein and Bohr argued face-to-face with an intensity and a mutual respect that is unusual in scientific controversy. Einstein would arrive each morning with a new thought experiment designed to show that quantum mechanics was either incomplete or inconsistent. Bohr would struggle to find the response, sometimes overnight, returning the next morning with the counter-argument. The records suggest that Bohr usually found the counter-argument, but not always quickly, and the arguments Einstein raised were always real and always required genuine thought to answer. The two men were not arguing about data or calculation. They were arguing about the nature of reality, and both of them were serious enough about the question to argue it with their full intellectual force for decades. In 1935, Einstein made what he believed was his most powerful argument. He wrote it up as a paper with two colleagues, Boris Podolsky and Nathan Rosen, and published it in the Physical Review under the title, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" The paper described a situation that has since become famous: two particles that have interacted and then been separated, allowed to travel far apart from each other, and then measured. In the quantum mechanical description, the two particles share a single wave function after their interaction, a combined wave function that cannot be decomposed into independent wave functions for the individual particles. They are entangled. Their properties are correlated in the quantum description in a specific way. When you measure the position of one particle, you instantly know the position of the other, because the wave function of the two-particle system specifies a precise relationship between their positions. When you measure the momentum of one, you instantly know the momentum of the other. Einstein, Podolsky, and Rosen, EPR, argued as follows. When you measure the position of particle 1, you instantly know the position of particle 2, which can be arbitrarily far away. But the measurement of particle 1 cannot have physically disturbed particle 2. The particles are far apart, and no signal can travel between them faster than light. Therefore, particle 2's position was real and definite before you measured particle 1. It had to be, because you can know it without disturbing it. But quantum mechanics does not assign a definite position to particle 2 before measurement. Quantum mechanics says particle 2 is in a superposition of positions until measured. Therefore, quantum mechanics is incomplete. It fails to describe the real, pre-existing position of particle 2. There must be hidden variables that specify the particle's real position, variables that quantum mechanics ignores. The argument was elegant, careful, and seemed to Einstein to be airtight. Bohr's response was published a few months later, also in the Physical Review, also titled with the words, "Can quantum mechanical description of physical reality be considered complete?" Bohr argued that EPR's argument depended on a specific definition of physical reality, a definition that assumed properties of a system were real and definite prior to measurement, and that this assumption was precisely what quantum mechanics challenged. The concept of the position of particle 2, prior to any measurement, was not a physically meaningful concept in Bohr's view. The entanglement between the particles meant that they constituted a single quantum system, and you could not talk about the properties of either particle independently. The measurement of particle 1 did not reveal a pre-existing property of particle 2. It established a relationship. It brought particle 2's property into being, in the sense that it created the conditions under which that property had a definite value. Bohr's response was, by his own standards, unusually dense and difficult to parse, and many physicists who read it were unsure whether it actually answered EPR or simply restated the Copenhagen philosophy in a way that seemed to avoid the question. Einstein was not satisfied. He continued to believe that quantum mechanics was incomplete. He continued to look for a deeper theory. He was still looking when he died in Princeton in 1955, having spent the last 2 decades of his life in a research program that most physicists considered a dead end. He never found the hidden variable theory he was looking for. And most of the physics community, in the years after his death, considered the EPR question essentially a philosophical one, interesting as a matter of interpretation but not experimentally decidable, not something that physics could actually test. The wave function was either a complete description of reality or it was not, but no experiment could tell you which, because any experimental outcome could be explained either by quantum mechanics with its irreducible randomness or by a hidden variable theory with its underlying determinism. The two pictures made the same predictions. The question seemed unanswerable. And then, in 1964, a 36-year-old Irish physicist named John Stuart Bell wrote a paper that proved this was wrong. The two pictures did not make the same predictions. With sufficient ingenuity, you could design an experiment that would give different results depending on whether quantum mechanics was correct or whether there was a local hidden variable theory underneath it. The question was experimentally decidable after all. And the way Bell showed this is one of the most beautiful pieces of reasoning in the history of physics. Bell was born in Belfast in 1928, the son of a horse dealer, and grew up in working-class Northern Ireland with a fascination for science that his family barely understood but actively supported. His mother reportedly told him that whatever he wanted to do with his life, she would back him, and what he wanted to do was physics. He won a scholarship to Queen's University Belfast, studied physics, went to work at the UK Atomic Energy Research Establishment, and eventually ended up at CERN in Geneva, where he spent most of his career working on accelerator design, which was his job, and thinking about the foundations of quantum mechanics, which was his passion, pursued in his spare time and on sabbaticals, in the margins of his official work. The foundations of quantum mechanics were not a fashionable research area in the early 1960s. The practical physicists, the ones building accelerators and calculating cross-sections and developing the experimental techniques that produced the particle physics results of that era, had little patience for philosophical questions about the interpretation of the wave function. The attitude was, shut up and calculate. The theory works. Stop worrying about what it means. Bell could not stop worrying about what it meant. He had read the EPR paper carefully, and he had read David Bohm's 1952 reformulation of the EPR argument in more concrete terms, and he had been thinking for years about whether Einstein's intuition might be right, whether there really was a local hidden variable theory that reproduced the predictions of quantum mechanics. He had also, in the early 1960s, read a 1932 proof by the mathematician John von Neumann that purported to show that hidden variable theories were impossible, that no hidden variable theory could reproduce all the predictions of quantum mechanics. This proof was widely accepted and widely cited. It had been one of the reasons most physicists felt the EPR question was settled in quantum mechanics' favor. Bell read von Neumann's proof and decided it was wrong. More precisely, he decided that von Neumann's proof contained an assumption that was mathematically natural but physically unjustified, an assumption that ruled out hidden variable theories not because they were physically impossible, but because von Neumann had inadvertently assumed they were. Bell published a paper in 1966 pointing this out and demonstrating that Bohm's 1952 hidden variable theory, which von Neumann's proof supposedly ruled out, was a perfectly valid hidden variable theory that reproduced quantum mechanics exactly, for a specific reason that von Neumann's proof did not cover. But before that paper was published, because of a delay in the journal that pushed publication back to 1966, Bell had already done the deeper work. In 1964, he had found his theorem, and the theorem said something that made the EPR debate experimentally decidable in a way nobody had previously found. The argument goes like this. Imagine two particles that have been prepared in an entangled state and then sent in opposite directions to two distant measuring devices. At each device, a measurement is made. Let us say a measurement of the spin of the particle along some axis, which can be oriented in any direction. The experimenter at each device can choose which direction to orient their measurement axis, and the outcome of the measurement is either spin up or spin down for the chosen axis. The two experimenters make their measurements at the same time, far apart from each other, so that no signal traveling at the speed of light or slower could communicate the result of one measurement to the other device before the other measurement is made. In quantum mechanics, the outcomes of the two measurements are correlated. They depend on the relative orientation of the two measurement axes in a specific way predicted by the quantum mechanical wave function for the entangled state. If the two axes are parallel, the outcomes are perfectly anti-correlated. If particle 1 is spin up, particle 2 is spin down, always, without exception. If the axes are perpendicular, the outcomes are uncorrelated. Knowing the result of one measurement tells you nothing about the result of the other. At intermediate angles, there is a specific quantitative correlation that varies with the angle in a way determined by the quantum mechanical prediction. Now consider a local hidden variable theory. In such a theory, each particle carries hidden variables that determine in advance, for every possible measurement axis, what outcome will be produced. The hidden variables are set at the moment the particles interact and separate, and they carry this information with them as they travel to the measuring devices. The particle does not need to communicate with its partner after separation, because everything is already determined. The correlations between the measurements arise not from any non-local connection, but from the shared history. The particles have carried, since they separated, instructions that tell each of them what to do for every possible measurement orientation. Bell asked, can such a local hidden variable theory reproduce the correlations predicted by quantum mechanics? And he showed, through a mathematical argument of remarkable simplicity, that the answer is no. There is an inequality, now called Bell's inequality, that constrains the correlations that any local hidden variable theory can produce. The inequality says that the correlations between measurements at different angles, added and subtracted in a specific combination, cannot exceed a certain value in any local hidden variable theory, and quantum mechanics predicts that entangled particles produce correlations that violate this inequality, that exceed the maximum allowed by any local hidden variable theory. The two pictures, quantum mechanics and local hidden variables, make different quantitative predictions. An experiment measuring the correlations can distinguish between them. Einstein's hidden variables, if they are local, if they do not involve any non-local influence traveling faster than light, cannot reproduce quantum mechanics. This is Bell's theorem, and it is hard to overstate how important it is. In a few pages of clear mathematics, Bell had transformed a seemingly philosophical question about the interpretation of quantum mechanics into an experimental question with a definite answer. Either quantum mechanics was correct and local hidden variable theories were wrong, or local hidden variable theories were correct and quantum mechanics was wrong, and you could tell which by doing the experiment. The question of whether Einstein or Bohr was right about the nature of reality was suddenly a laboratory question. Bell published the paper in 1964 in a new journal called Physics, which had only a small circulation and was not widely read. The paper sat largely unnoticed for several years. Bell continued his accelerator work at CERN. The physics community continued to assume the foundations of quantum mechanics were a settled question not worth worrying about. And then, slowly, people started reading the paper, and the people who read it realized what it meant, and the race to do the experiment began. The first serious experimental test of Bell's inequality was performed by John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, the CHSH team, in the early 1970s. Clauser, working at Berkeley, built an apparatus that used pairs of photons produced in an atomic cascade, a process in which calcium atoms excited by a laser emit two photons in sequence that are polarization entangled. The polarization of a photon, the direction in which its electric field oscillates, is the relevant property being measured, and it plays the role of spin in Bell's original argument. Clauser measured the correlations between the polarizations of the two photons for various orientations of the polarizing analyzers and compared the result to the Bell inequality. The result violated the Bell inequality. Quantum mechanics was right. Local hidden variables were wrong. The experiment was not perfect. There were what physicists called loopholes, assumptions that the experiment had to make and that a sufficiently clever hidden variable theory might exploit. But the result was a clear, strong violation of the inequality, exactly as quantum mechanics predicted. The most important early experiments were those performed by Alain Aspect and his collaborators at the Institut d'Optique in Orsay, France. In the early 1980s, Aspect was a young physicist who had become fascinated by Bell's theorem as a graduate student and had decided to perform the definitive test. He worked for years building an improved apparatus that addressed the most serious loopholes in Clauser's experiment. The critical improvement was the ability to change the orientation of the polarizing analyzers while the photons were in flight, after they had been emitted and before they had reached the detectors. This addressed the locality loophole, the concern that the hidden variables might somehow read the setting of the analyzer and adjust the photon's behavior accordingly. If the setting is changed after the photon has been emitted and while it is traveling to the detector, there is no way for the photon to carry information about the setting from the emission point. The information about the setting was not available when the photon left. By rapidly switching the analyzer settings during the photon's flight, Aspect ensured that no signal traveling at light speed or below could carry information about one photon's measurement setting to the other photon before it was measured. Aspect's 1982 experiment violated the Bell inequality even more clearly than Clauser's, with the locality loophole closed. The result was statistically overwhelming. Quantum mechanics was confirmed, local hidden variables were ruled out. The physics community took notice. The paper was published in Physical Review Letters and was recognized as a landmark. Einstein had been wrong. The universe was not locally real in the sense Einstein had required, the sense in which particles have definite pre-existing properties that determine measurement outcomes locally, without any non-local influence. The word non-local here requires care, because it is easy to misunderstand and the misunderstanding matters. Entanglement does not allow you to send information faster than light. This is crucial and has been proven rigorously. When you measure particle 1 and get a result, your result is random, you cannot control it. When your partner measures particle 2 far away, their result is also random. The correlation between your results is only apparent when you compare notes, when you bring your data together by some means that is limited to the speed of light. You cannot use the entanglement correlation to send a message faster than light, because the outcome of each individual measurement is random and uncontrollable. Entanglement cannot be used to communicate. Special relativity is safe, but something non-local is happening. The correlations between the measurement results, the specific pattern of correlations violating Bell's inequality, cannot be explained by any local mechanism, any mechanism that involves each particle carrying pre-existing properties set at the moment they separated. When you measure particle 1 and get spin-up, particle 2's measurement result is influenced, constrained, in a way that cannot be accounted for by any information the particle carried from its point of origin. The particles are correlated in a way that requires, not merely allows, but requires a non-local connection. The connection is real. It is just not exploitable for communication. This is what Einstein could not accept, and it is genuinely hard to accept. Einstein's intuitions about physics were so powerful and so often right that it is tempting to find some way to rescue his view, to find an interpretation of the experiments that restores locality and realism. Physicists have tried. They have tried hard. The many worlds interpretation, the view that all quantum outcomes occur in branching parallel universes, restores determinism, but not locality in any simple sense. Bohm's pilot wave theory restores realism. Particles have definite positions, but at the cost of an explicitly non-local guidance equation. String theory has not resolved the issue. Loop quantum gravity has not resolved it. Every serious attempt to restore locality and realism to quantum mechanics has either failed or required giving up something else that seems equally essential. Bell's theorem closes off the escape routes, one by one, with the authority of mathematics. The experimental tests of Bell's inequality have continued and improved for 60 years since Bell's paper, each generation closing loopholes that the previous generation left open. The locality loophole, the detection loophole, the concern that the detectors might not be sampling photons fairly, only capturing a biased subset, and the freedom of choice loophole, the concern that the settings of the measuring devices might somehow be correlated with the hidden variables of the particles, have all been addressed in increasingly sophisticated experiments. In 2015, 3 experiments in Delft, in Vienna, and at NIST in Boulder, Colorado, performed what are called loophole-free Bell tests, experiments that closed all major loopholes simultaneously for the first time. The violations of Bell's inequality were confirmed with statistical confidence of more than 5 sigma, the gold standard in physics for a definitive result. There is no room left for doubt. The universe violates Bell's inequality. Local realism is false. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger, 3 of the central figures in the experimental development of entanglement physics, for their experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. The citation was unusually clear about what the work had established. It had proven that quantum mechanics correctly described a feature of the universe that violated local realism, and it had opened the door to practical technologies based on quantum entanglement. The Nobel Committee does not often give prizes for results that are philosophically disturbing. This time they did. Anton Zeilinger, the Austrian physicist who received the prize, had spent decades not just testing Bell's inequalities, but pushing quantum entanglement into new territory, demonstrating quantum teleportation, quantum cryptography, and quantum communication over increasingly long distances. His group teleported quantum states between particles in laboratories, then between particles separated by kilometers across Vienna, then between particles separated by hundreds of kilometers using fiber optic cables and free space links, eventually demonstrating entanglement between particles on the ground and particles aboard a satellite. Zeilinger and his collaborators, and the parallel group in China led by Jianwei Pan, Zeilinger's former student, have built what are essentially the first components of a quantum internet, a network that uses entanglement to achieve communication security that is guaranteed by the laws of physics rather than by the difficulty of computation. Quantum cryptography, more precisely quantum key distribution, uses entanglement to distribute encryption keys between 2 parties in a way that is provably secure against eavesdropping. The security comes directly from the quantum mechanical properties that Bell's theorem explores. If an eavesdropper intercepts the quantum channel and measures the particles, the act of measurement disturbs the quantum state, because measuring a quantum system changes it, unavoidably, and the disturbance shows up as errors in the key. Alice and Bob, comparing a subset of their key bits over an ordinary classical channel, can detect any eavesdropping by looking for these errors. If the error rate is below a threshold, the key is secure. Above it, they discard it and try again. The security of the key does not depend on any computational assumption. It is not based on the difficulty of factoring large numbers or solving discrete logarithms, which could in principle be broken by a sufficiently powerful computer. It is based on the laws of physics, specifically on the fact that quantum measurement disturbs quantum states. The first quantum key distribution systems have been demonstrated experimentally over distances of hundreds of kilometers, and the Chinese satellite Messias, which Zeilinger's group used for their long-distance entanglement experiments, has demonstrated quantum key distribution from space. Quantum computing is the other technology that quantum entanglement makes possible, and it is the one that has attracted the most investment and the most public attention. A quantum computer uses quantum bits, qubits, instead of classical bits. A classical bit is always either 0 or 1. A qubit can be in a superposition of 0 and 1 simultaneously, which means it encodes both values at once. 2 qubits can be in a superposition of all 4 possible 2-bit states simultaneously. 10 qubits can be in a superposition of all 1,024 possible 10-bit states simultaneously. 50 qubits can be in a superposition of a quadrillion states simultaneously. The exponential growth of the state space with the number of qubits is what gives quantum computers their potential power. A quantum computation can, in principle, process all possible inputs simultaneously, finding the answer through a clever interference of the quantum amplitudes without having to try each input sequentially. Entanglement is essential to quantum computing. The ability to create entangled qubits whose quantum states are correlated, is what allows a quantum computer to perform computations that involve correlations between different parts of the input, which is precisely what many important computational problems require. Algorithms like Shor's algorithm for factoring large numbers, which would break the encryption that secures most internet communication if run on a large enough quantum computer, and Grover's algorithm for searching unsorted databases, achieve their speedups by exploiting entanglement in sophisticated ways. The development of practical, large-scale quantum computers is one of the most significant technological challenges of the current era, pursued by IBM and Google and Microsoft and Amazon and dozens of startups and national laboratories around the world. As of the mid-2020s, the largest quantum computers have on the order of 1,000 qubits, but maintaining the quantum coherence required for computation, keeping the qubits from decohering, from losing their quantum properties through interactions with the environment, remains the central engineering challenge. The decoherence problem is itself intimately connected to the measurement problem and to the question of what quantum mechanics means. When a quantum system interacts with its environment, the surrounding atoms, the electromagnetic field, the vibrations of the apparatus, it becomes entangled with the environment. The quantum superposition of the system spreads into the enormous quantum superposition of the system plus environment. From the perspective of anyone measuring only the system, the superposition appears to have collapsed. The quantum coherence has been lost into the environment, too dilute to observe. This process, called decoherence, explains why the macroscopic world appears classical, why Schrödinger's cat is not both alive and dead, why large objects have definite positions rather than quantum superpositions. The entanglement of macroscopic systems with their environments is so rapid and so thorough that any quantum superposition disappears into the environment in fractions of a nanosecond, and what remains looks exactly like a definite classical outcome. Decoherence does not solve the measurement problem. It does not tell you which of the many possible outcomes the universe actually picked, or whether the concept of a definite outcome is even correct. But it explains why quantum superpositions are not observable in everyday life, and why maintaining quantum coherence in a quantum computer is so difficult. The quantum computer must be isolated from its environment with extraordinary care, which is why quantum computers require temperatures within hundredths of a degree of absolute zero, colder than the average temperature of outer space, and elaborate electromagnetic shielding. The connection between entanglement, decoherence, and the interpretation of quantum mechanics brings us back to the deepest question raised by Bell's theorem. What does the violation of local realism mean about the nature of reality? This is not a settled question. Physicists who have thought about it the most carefully disagree, sometimes sharply, but the space of disagreement has been constrained by Bell's theorem in a way that it was not before. Before Bell, you could believe in a local realistic universe with hidden variables, and Einstein's intuitions would be preserved. After Bell, you cannot. You must give up either locality or realism, and every serious interpretation of quantum mechanics gives up one or both. The Copenhagen interpretation gives up realism, or at least it refuses to commit to any picture of what is happening when no measurement is being made. Quantum mechanics describes measurement outcomes, not underlying reality. What the particle is doing between measurements is not a question that physics answers. The wave function is a tool for calculating probabilities, not a description of physical reality. Many physicists find this position pragmatically useful and philosophically unsatisfying simultaneously. It is the shut up and calculate position taken seriously. It works. It produces correct predictions. It does not tell you what the universe is doing. The many worlds interpretation, developed by Hugh Everett in his 1957 Princeton PhD thesis, and long ignored before being rediscovered and taken seriously by physicists including Bryce DeWitt and later David Deutsch, gives up the collapse of the wave function entirely. In the many worlds view, the wave function never collapses. It just keeps evolving according to the Schrödinger equation, always, without exception. When a measurement is made and the result appears to be one definite outcome, what has actually happened is that the measuring device and the observer have become entangled with the quantum system, and the combined wave function now contains multiple branches, one for each possible outcome, each branch containing a different version of the observer seeing a different result. All outcomes happen, all branches exist, all versions of the observer see a definite result in their own branch. The randomness of quantum mechanics in this view is the subjective experience of finding yourself in one branch rather than another, an experience that feels random even though the full wave function evolves deterministically. The many worlds interpretation is local. It does not require non-local influences, but it requires an enormous ontological commitment, an infinite branching multiverse of parallel realities, all equally real, all containing versions of you that made different decisions and saw different quantum outcomes. Bohm's pilot wave theory, also called de Broglie-Bohm theory or Bohmian mechanics, takes the opposite approach. It gives up locality while preserving realism. In Bohm's theory, Particles have definite positions at all times, and the wave function is a real physical field, the pilot wave, that guides the particles through space according to a specific equation of motion. The pilot wave is explicitly non-local. The equation of motion for each particle depends on the wave function of the entire system, including the positions of all other particles, instantaneously, regardless of distance. The correlations that violate Bell's inequality are produced by this non-local guidance. The pilot wave tells particle 2 what to do based on what is happening to particle 1, instantaneously across any distance. Bohm's theory reproduces all the predictions of standard quantum mechanics exactly. It is not an alternative to quantum mechanics. It is a different version of quantum mechanics with an explicit ontology, an explicit picture of what the world is actually doing. Many physicists find it compelling as an interpretation. Most find the explicit non-locality in the guidance equation aesthetically unappealing, a high price to pay for ontological clarity. There are other interpretations: relational quantum mechanics, QBism, the consistent histories approach, the transactional interpretation, each representing a different philosophical response to the measurement problem and to the non-locality revealed by Bell's theorem. None of them has achieved consensus, none of them has made a novel experimental prediction that distinguished it from the others. The physics works, quantum mechanics predicts the right numbers, tested to extraordinary precision, and the interpretations all agree on what the numbers are while disagreeing profoundly about what those numbers mean. The question of what is actually happening at the quantum level when entangled particles are measured remains one of the deepest and least settled questions in the foundations of physics. What is settled, and this is worth being clear about, is what Bell's theorem demonstrated. It demonstrated that any theory of the world that is both local and realistic, that assigns definite pre-existing properties to particles, and requires that no influence travels faster than light, cannot reproduce the predictions of quantum mechanics, and quantum mechanics predictions are correct. Therefore, the world is not both local and realistic. Something has to give. Either particles do not have definite pre-existing properties, they do not have definite spins before they are measured, or influences can travel between entangled particles faster than light, instantaneous, but uncommunicable. Both options are deeply strange. Both options contradict intuitions that feel foundational to rational thought about the physical world. And the universe apparently does not care about our intuitions. Einstein's intuitions were extraordinary. They were the source of some of the most important discoveries in the history of physics. They were right about the photoelectric effect, right about the special theory of relativity, right about general relativity, right about Brownian motion, right about stimulated emission of radiation. They were wrong about quantum entanglement, wrong in a way that took 30 years after his death to demonstrate experimentally, but wrong definitively, wrong completely, wrong in a way that cannot be papered over or reinterpreted as secretly correct. The universe is non-local. Spooky action at a distance is real. The most creative and most powerful physical intuition in the history of science was confronted with a feature of reality it found unacceptable, and reality did not accommodate it. There is something important and somewhat uncomfortable in this about the nature of scientific progress. Einstein's intuitions were not just arbitrarily wrong. They were wrong in a specific way. They assumed that the world at its most fundamental level should have the same properties that it has at the scales we can directly perceive. Locality and realism are features of the classical world that we evolved to navigate, a world in which objects have definite positions, in which distant objects do not influence each other instantaneously, in which the properties of things exist whether or not anyone is looking at them. These features of the classical world are so deeply embedded in our perceptual experience and our cognitive architecture that they feel not just empirically true but logically necessary. They feel like the conditions of possibility for rational thought itself. Einstein felt this. He said explicitly that he could not conceive of a universe in which distant entangled particles were correlated in ways that violated local realism. His inability to conceive of it was not a failure of imagination. It was the accurate report of an extraordinarily sophisticated mind telling him what it could and could not accommodate. The universe is not obligated to accommodate it. The universe does what it does, and if what it does is strange beyond the capacity of any human mind to hold comfortably, that is not a problem with the universe. It is a feature of the universe. The strangeness is real. The correlations that violate Bell's inequality are real. The entanglement that connects distant particles is real. The fact that we cannot picture it, cannot make it fit into any model of the world that our evolved minds find intuitive. That is our problem, not the universe's. Physics, at its frontier, is in the business of discovering features of reality that are not accessible to unaided intuition, and entanglement is perhaps the clearest example of a feature of reality that resists not just intuitive understanding, but even the gentler demand of visualizability. You cannot draw a picture of entanglement that captures what is actually happening. You can write the equations, you can confirm the predictions, you cannot picture it. The person who was perhaps most comfortable with this was John Bell himself. Bell spent his career at CERN as an accelerator physicist, and he pursued the foundations of quantum mechanics in the margins, in the spaces between his official work, with a modesty about his own contribution that was characteristic. He did not think of himself as having solved a great problem. He thought of himself as having sharpened a question, as having taken a vague philosophical dispute and turned it into a precise mathematical inequality that experiments could test. He was pleased when the experiments confirmed the violation. He was not triumphant. He continued to find the implications of his theorem disturbing. He believed that quantum mechanics was probably not the final word, that the non-locality it required was a sign that something deeper was going on, something that a future, more complete theory would eventually illuminate. He did not know what that theory would look like. He was modest about his ability to guess. He thought the situation was strange and that the strangeness should be acknowledged rather than papered over with philosophical sloganeering. Bell died suddenly of a stroke in 1990, 2 years before a Nobel Prize was rumored to be in consideration for him. He did not live to see the loophole-free Bell tests of 2015 or the Nobel Prize of 2022. He did not live to see quantum cryptography become a working technology, or quantum computing become a multi-billion-dollar industry, or quantum entanglement become a standard tool in the laboratory. He lived long enough to see the violation of his inequality confirmed, repeatedly, in increasingly precise experiments. He lived long enough to know that he had been right, that the question was answerable, and that the answer was unambiguous. He said, late in his life, that the most important message of his theorem was that the world was genuinely strange, in a way that no familiar picture could capture, and that this strangeness deserved to be taken seriously rather than dissolved by philosophical convention. He was right. The world is genuinely strange. Two particles, once they have interacted, can remain connected across any distance in a way that no local model can explain. The connection is real. It has been measured. Its properties have been characterized. It is being used to build technologies. The connection is also deeply mysterious. It does not fit into any picture of the world that either common sense or classical physics provides. It is one of those places where the universe, examined carefully enough, turns out to be simply different from what we expected, in a way that is not merely quantitatively surprising, but qualitatively alien. A place where the question, but what is really happening, does not have a universally agreed-upon answer, where the greatest minds who have examined it have come away with different views, where the strangeness is irreducible and probably permanent. Einstein asked the question, in 1935, in a paper he thought would destroy quantum mechanics. Bell found the way to answer it, in 1964, in a paper he wrote in the margins of his official work. The experimenters answered it, over 50 years of increasingly precise measurements, in experiments that closed every loophole and ruled out every local alternative. And the answer is, Einstein was wrong. Quantum mechanics is right. The universe is not locally real. Two particles can share a connection that transcends any ordinary notion of distance or separation, a connection that makes a measurement on one of them instantly relevant to the other, regardless of where the other is, in a way that no hidden variables can explain. Spooky action at a distance. Einstein's reductio ad absurdum, the thing he offered as proof that quantum mechanics could not be right. It is real. It has been confirmed. It is the subject of Nobel Prizes and quantum computers and quantum cryptography, and the most sophisticated experiments in the history of physics. And it means that the universe, at its most fundamental level, is stranger than the greatest physicist who ever lived could bring himself to believe. We live in that universe. We are made of entangled particles. The atoms of your body are part of a quantum system that extends in principle across the entire universe, connected by entanglements established in the interactions of your particles with the world around you. The entanglement is fragile at macroscopic scales. Decoherence destroys it almost instantly. But it is real. The universe is not locally real. The fabric of reality, at the level where it cannot be simplified or approximated or averaged into something familiar, is woven from something that does not fit into any picture of the world that intuition provides. John Bell asked whether the universe was spooky. The universe said yes.